Hello everyone, welcome to the Computer Networks lecture series. In this particular session, we'll study about bandwidth utilization using multiplexing, and the other topic is spreading. So what is multiplexing? Multiplexing is a set of techniques that allows the simultaneous transmission of multiple signals across a single data link. So we have a single data link. That data link may be a wired data link or a wireless data link, and we pass multiple signals through that particular single link. So that is how we make a good utilization of the particular link. So here, to understand this with an example, let us understand this with an example. So here, suppose we have a highway having two roads, one going towards the left, other going towards the right. So at this moment, what we observe is one vehicle is passing through each road on a particular way. Although the capacity of this and any of the way is large, but only because only one vehicle is passing. Now what we can do is we can make two lanes across each of the roads, so that now two vehicles can pass easily instead of one. So this is the capacity. So in this case, we make a more efficient use of this particular highway by making two lanes. So this is what multiplexing is around. So to make an efficient use of the available bandwidth, we use multiplexing. So here we can see there is a single link, and this link is shared by various channels. On the left side, we have n inputs which are multiplexed into a single link, and on the right side we have the demux, that is the demultiplexer. It actually separates out each output. So here on the left side we have n inputs, on the right side we have n outputs, and they are sharing a single link. So suppose if we have 4 input channels, so 4 input channels, they are using the same link. So instead of one channel using that link, there are many number of channels which can use this particular link. So there are various categories of multiplexing technique. So the first one, as we can see, is a frequency division multiplexing, that is FDM. Then we have wavelength division multiplexing, WDM, and we have time division multiplexing, TDM. These two techniques, that is FDM and WDM, they are analog, and this one, digital time division multiplexing, is digital technique. So what is frequency division multiplexing? So in frequency division multiplexing, it is used when a link bandwidth is greater than the combined bandwidths of signal to be transmitted. So we have a single link, and the bandwidth which is available for that particular link is very large, and the channels which are transmitting the signals, their bandwidth is very low. So here we have this example. So this is the link in the center, and on the left side we have 4 channels which are transmitting the data, and the right side we have 4 channels which are actually receiving the data. So this is the bandwidth of the link. This arrow, this shows the wide link which is available. Now channel 1 requires only a part of that particular link. The bandwidth is very less. Okay, so it requires just small portion of the bandwidth. So now we can occupy 4 channels: channel 1, channel 2, channel 3, channel 4. So these 4 channels, they are using the same link to transmit and receive the data. So this is how frequency division multiplexing is used. So the link bandwidth is very large, and the channel requires a very small portion of the bandwidth. So this is 4 channels are using the same particular link. So in FDM, signals from each sending device, they are modulated by different frequencies, and they are combined into a single composite signal. So what is the meaning of this? So here on the left side we have 4 signals. Now these 4 signals are the information which we want to send. So these are also called as the baseband signals. And here what we do is we use 3 different carrier frequencies, F1, F2, F3, having different frequencies, and this particular carrier signals, they are modulated by this bandwidth baseband signals, and we have this particular result. These 3 signals, they are combined. Okay, they are actually modulated and they are combined together, and on the right side we have this combined signal. This is sent through the link, and on the receiving side we demodulate the signals so that they are received properly. So this is the combined signal. Okay. Now next is the wavelength division multiplexing. So wavelength division multiplexing, it utilizes the high data rate capability of fiber optic cables. So fiber optic cables, they have a very large bandwidth. So we utilize the bandwidth of this fiber optic cables by using the wavelength division multiplexing. So fiber optic cable, they have of course very high data rate as compared to the cables that is the metallic cables. So WDM, it prevents bandwidth waste by combining multiple lines into one. So WDM, that is wavelength division multiplexing, is similar to frequency division multiplexing. Only the difference is that in case of WDM, wavelength division multiplexing, it involves the optical signals and not the electrical signals. So here how it works. So here on the left side we have senders, and on the right side we have the receivers. So these are the three signals. So I have used different colors to represent different wavelengths. So blue signal, green and orange, these are three different signals. And because as we know, the wavelength depends on the color, so three different signals are used. So we have lambda 1, the wavelength of the first signal, lambda 2 the second, lambda 3 the third one. So they are sent through the multiplexer, okay, and they are combined into this particular link. They will not interfere with each other because their wavelength is totally different. So at the receiving side they are demultiplexed and they are received by the proper receiver. So this wavelength division multiplexing is utilized in fiber optic systems. So here we have this fiber optic cable which connects the two the senders and the receivers. So here these three signals are combined, they are sent, and at the receiving they are separated. So this is how the wavelength division multiplexing works. Now next is time division multiplexing. Now time division multiplexing is a digital processing which enables several connections to share the high bandwidth of the link. So this let's see what occurs. So this is not similar to FDM. FDM, it shares the bandwidth, while TDM, time division multiplexing, it shares the time. Now in each connection, in this case, it occupies a specific portion of time on the link. So TDM, it allows multiple connections to utilize the same link by dividing into time slots. So here time is divided, frequency is not divided. So let us see how it works. So on the left side we have 1 2 3 4 senders, and on the right side we have 1 2 3 4 the receivers. So we divide this particular channel in terms of time. So the first portion of the time slot, so we create various time slots. The first slot is given to the first host, the second time slot is given to the second host, so it gets the entire bandwidth but only for a short time period. So this is the third one, this is the fourth one. So in this way every channel gets its time of the its share of the time slot. So here frequency is not divided but time is divided. So it gets whatever channel, it gets the time, it gets the entire bandwidth. So it gets the entire bandwidth for a very short interval of a time. So this is how time division multiplexing works. Now we have something called as synchronous TDM. So in case of synchronous TDM, we have fixed allotment. So each input connection has an allotment in the output, even if it is not sending any data. So suppose if we have 4 channels, one other channel does not wants to send the data, that time slot is wasted because that was available to that particular channel, it is not sending, so that time slot nobody will send, okay, that is actually wasted. Then time slot division. So as we know, input data is divided into units, each occupying one time slot in the output. So output time slots are shorter than by a factor of n if there are n number of connections, that we'll see in the diagram. Now we have something called as a frame. So what is the meaning of a frame? Suppose if there are 4 channels which are sending the data, so if we combine all the data coming from all the 4 if we combine the data coming from the 4 channels, that will make up a single frame. Okay, that is how we make up the frame. Now output data rate. So output data rate must be n times the data rate of each connection to maintain the data flow. So suppose if we have 4 input, so the link's data rate must be 4 times okay, because there are four, it must actually support 4 channels, so it must be 4 times faster as compared to the each particular channel. So in this case, input data is divided into fixed size blocks. So this is the input data, it is divided into fixed size units. So as we can see, the first one is divided into A1, A2, A3, second is B1, B2, B3, third is C1, C2, C3. So this A1, B1, C1, they are of same size, A2, B2, C2, they are of same size, A3, B3, C3, they are of the same size. So we divide the input data into slots. Then each input connection is connected to a time division multiplexer. So this is a time division multiplexer, and each input connection gets a time slot to send the data. So first A will get the chance, so A will send first slot. In the first slot, it will get the chance to send the data. So it sends A1, then we have B1, then we have C1. So this entire thing, that is A1, B1, C1 combined, it becomes the frame, the first frame. Of course, the second frame will contain A2, B2, C2. The third will contain A3, B3, C3, and so on. So in this given case, the speed of the link is 3 times faster as compared to the link of each connection. So here, if the speed is x of each connection, then the speed of the link is 3 times the x. Then also in the given case, the time period of the link is 1/3. So it is 1 divided by 3. It is not 3 times, it is 1/3 the time period of each connection. So it must be faster, so time period becomes less. So if the time period of each link is t, then the time period of this particular if the time period of the channel is t, then the time period of link becomes t by 3, so that all the data gets collected at the same time. Then next is the data rate management. So what is data rate management? So in many situations, we may not get the same data rate from each and every channel. Okay, so if there is any disparity, so how to manage those? So in order to handle different data rates, we use 3 strategies. The first is multi-level multiplexing, second is multiple slot allocation, and the third is pulse stuffing. So first of all, what is the meaning of multiplexing? So in case of simple multiplexing, if the speed of the link is 160 kbps, kilobits per second, then if there are 4 channels, every channel will have a speed of 40 kbps, so that 40 plus 40 plus 40 plus 40 becomes 160. So this is how the multiplexing is done. This is a single level multiplexing. What we are going to study is multi-level multiplexing. So what is this? So in this case, suppose if we have 5 channels such that 3 are having a speed of 40 kbps, but 2 are having a speed of 20 kbps. So what to do in this case is that we introduce one more multiplexer here, which combines this 220 kbps signal into 140 kbps. So it becomes 440 kbps. So here we have 440 kbps. Okay, and here we are using a multi-level multiplexing. So there are 2 levels. One level, it combines 20 kbps signals, and the final one, the 40 kbps signals into 160 kbps signal. So this is multi-level multiplexing. Then we have multiple slot multiplexing. So in multiple slot multiplexing, again this is a simple multiplexing where we have the link speed as 125 kbps, and the inputs are 5 channels having each 25 kbps speed. Now it may happen that, suppose if we have a channel having a speed of 50 kbps, now we cannot combine here directly, so we need to split this 50 kbps into 2 25 kbps. So we use a demultiplexer actually. So this is how we have a multiple slot multiplexing. This is how it works. Then finally we have the topic, that is pulse stuffing. So in case of pulse stuffing, so this is a simple multiplexing where we have the link capacity, the link bandwidth as the link speed as 200 kbps, and we have 4 channels each of 50 kbps. Now suppose one of the channel is having a speed of 44 kbps, but we require 50 kbps. Now this cannot be done, so what we do is we use a thing called as pulse stuffing. Okay, so pulse stuffing, it actually adjusts the input speed to 50 kbps, so that we have this particular thing. So this is what is the pulse stuffing is around. Now the next main topic is the spread spectrum. So what does it do? So it combines signals to fit into larger bandwidth. So initial signal may be of less bandwidth, the final it becomes of larger bandwidth. Now this particular spreading technique is used for wireless applications. Now it prioritizes the security over bandwidth. So we want to have security. So to gain security, we actually have to increase the bandwidth. Now it uses air or vacuum as the communication medium. Now what is this? What happens? Actually, this is the bandwidth of the original signal. Okay, and it goes through the spreading process using a particular spreading code, and we get the spreaded signal. So on the right we had the spread signal. Now the first technique in this case is the frequency hopping spread spectrum, FHSS. So in this case, the frequency hopping spread spectrum, it uses a technique in which m different carrier frequencies are used. So these frequencies are modulated by a source signal one at a time. Okay, and because of this particular thing, the bandwidth of the occupied by source after spreading becomes very large. So this on the right side, B is the bandwidth of the signal, and BFHSS is the bandwidth of the signal which we get as the output, the spread signal. Now here it works, how it works. So we have the original signal. This signal is combined with a frequency synthesizer. So how it gets? So here we have this pseudo random code generator. So whatever input signal we have, it produces a signal, it produces a frequency. So here we can see there are 8 frequencies. For input 000, the frequency is 100 kilohertz. For 001, the frequency is 200 kilohertz. So whatever input we are getting, this input is actually modulated by this, it is sent through this particular carrier frequency. So this is how we get the spreaded signal. So suppose now, if we have the input as 001, then this frequency selected is 200 kilohertz is selected as the carrier frequency, and if the input is 101, we have 600 kilohertz as the carrier frequency. So this is how it is done. Now if we combine frequency division multiplexing with frequency hopping spread spectrum, this is what we have. In case of FDM, we have this different frequencies, okay, F1, F2, F3, F4. So every channel gets its share of frequency. So channel 1 gets frequency F1, channel 2 F2, channel 3 F3, and channel 4 F4. So in FDM, for given case, each station, that is each channel, it utilizes 1/4 of the bandwidth, and the allocation is fixed. So if channel 1 it is given the frequency F1, so that is fixed, it won't be given F2, F3 or F4. And if channel 2 is given F2, it is not given any other frequency, so allocation is fixed, but only one part of the allocation is, one part of the frequency is given. Now in case of frequency hopping spread spectrum, as we can see, channel 1, it gets frequency F1 for a particular time period, then it hops to F2, it hops to F3, it hops to F4. Then channel 2 has this particular sequence. It sends the data for frequency F2 first, then F3, then F4, then F1, and so on. So here what happens in FHSS, for a given case, each station, it utilizes 1/4 of the bandwidth, but the allocation changes by half to of the allocation is not fixed. So at the bottom row, we see that channel 1, it transmits the signal with frequency F1 for a particular time, then the frequency hops to F2, then F3, then F4. So allocation is not fixed. Now next is DSSS, that is a direct sequence spread spectrum. So it expands the bandwidth of the original signal. Now in this case, each data bit is replaced with n bits using a spreading code. So we have a spreading code having some bit combination, and the original information is spread using this particular spreading code. So each bit is assigned a code of n bits, which we call it as chips. We'll say this, the chip rate is n times the data rate of the original data bit. Okay, so let us see with this example. Okay, this is actually a diagram. So this is the original signal is applied with the chip sequence and we get the spread signal. So on the left side we have the original signal, it is combined with the chip sequence and we get the output as in the form of a spread signal. So this is the example. Okay, so here this is the input signal 1 0 1. So this is our input signal, and next this is the spreading code. Okay, this is the chip, what we say. Okay, so this is spreading code. Now we combine the original signal with the spreading code and we get this. Okay, so this green wave which we are getting, it is the output, it is the spread code. We can make out when it is 1 we get the same thing, when it is 0 we get the complement of the spreading code. That is what we are getting. So this is how direct sequence spread spectrum works. Okay, the original signal, the spreading code and the spread signal. So that's all for this particular session. Thanks for watching. Do join for us for the next video.